Hi, this is Rena Lee from Daegu International School Peer Tutoring Club. Today, this is our second video for Chapter 1, Section 1, Limits and Continuity. We're gonna learn about discontinuity this time, so let's start right away. There are 3 discontinuity that we're gonna learn about, but there are extra 1 discontinuity, which is a special occasion discontinuity that occurs not so often, but it is also essential to know. So let's start. The first one is called removable point discontinuity. The conditions, which is also the reason why we identify some function as including some discontinuity. For this conditions, you really have to memorize this able to write the FRQ well. You have to know how to explain why you found this discontinuity and why you find the answer that you found for the FRQ. So you 100% have to memorize all these conditions that I provide you today. So the conditions, the reason of removable point discontinuity, you can find when, if for some function fx at x equals c, then limits of x towards c of the function equals L, but fc is undefined, or limits of x towards c of the function equals L, but f of c is not equal to L. This turns out that fx has a removable point discontinuity, which is also called as hole at c, L. For the last video, I introduced you about the hole, which looks like this. Right here that I drew a hole right over here. It's called a hole. So we define that if this happened here in this function fx, then there's a hole, which means there's a discontinuity. The second one is called jump discontinuity. If for some function fx at x equals c, then limit of x towards c minus of the function equals L, 1, and limits of x towards c plus of the function equals L2, where L1 is not equal to L2, regardless of f of c. Then this turns out that fx has jump discontinuity at x equals c. This depends on your teacher, but Mr. Coleman doesn't actually define jump discontinuity as a break, but some other teachers, they could call this as break. So just as a reminder, this looks like, it probably looks like this on your graph. This is called jump. Can you see this? This graph and this graph is not touching. It jumped. It's pretty easy to know, right? So the next one is called infinite discontinuity. If for some function fx at x equals c, then limits of x towards c minus of the function equals infinite or negative infinity, or limits of x towards c plus of the function equals infinity or negative infinity. This turns out that fx, which means a function, has an infinite discontinuity, which is also known as vertical asymptote at x equals c. As you all know, probably, vertical asymptote looks like this. and right here it is C. If vertical asymptotes occurs at your function, then your graph probably looks like this. Got it? And then this one's the special occasion occurring discontinuity is called oscillating discontinuity. For a function fx equals sine of 1 over x, then limits of x towards 0 of function equals dne. So this has specific function given for the discontinuity. It always happens for every time if fx equals sine over 1 over x, then it turns out that there is oscillating discontinuity. This also means that if this function turns out limits of x towards 0 of sine over 1 over x, then it is dne, which should look like, if there's a graph, then it probably looks like crazy right here. Can you see this? You can't define the exact point in this line graph because, as you can see, it is very complicated to just pick out some specific point over here. It's just going all over the place. Okay, so let's try some example questions. This is a graph given, and all you have to do is does a graph continue or not at given points over here. Pause the video and then try first. So at x equals -4, which is over here, it is infinite discontinuity. Because as you can see, the line is kept getting up over here, and we don't know when it stops. It goes infinite. That's why it is infinite discontinuity at x equals -4. And then number 2, at x equals 0, here, we can see that the function is not touching each other, but going in opposite directions. So at this point, we can see that there's a vertical asymptote. Which also turns out that it has infinite discontinuity. At x equals 6, which is over here, you can see a hole here. I drew it for you. And it turns out that there's removable point discontinuity. But not only this, you can also see that there is a jump discontinuity, because even though it stops over here by the hole, it starts from the other position, which is over here. It jumped. That's why, even though we can see that there's a hole, it is more likable to say there is a jump discontinuity. So you have to know how to solve this not only by graph but also algebraically. So I prepared another question for you. So using the definition of continuity at a point, discuss the continuity of the following function. Pause it and then try first, and then we'll talk about the answers. Okay, we'll start. First of all, we have to calculate that at x equals -2, limits of x towards -2 minus of the function x plus 2 equals 0, which is not equal to limits of x towards -2 plus of the function, which is x squared over 2 equals 0. You can see that they are not equal. This turns out that fx is not continuous by jump discontinuity. Because the value that you got by plugging these numbers in is not equal. Next step, you have to calculate at x equals 2, limits of x towards 2 minus of x squared over 2 equals 2. This is equals to limits of x towards 2 plus of the function, which is 2, equals 2. Which turns out that their values are equal. It also equals to f2. This turns out that, as a conclusion, fx is continuous on -infinity until -2 with -2 to infinity. This is it. Thank you for watching my video, and then I will come back with our third video. Thank you for watching and stay tuned.